9-5, base e and natural logs. So the natural base e is actually an irrational number. It's approximately 2.71828 and so forth. It's a number like pi that is never ending. That decimal will keep on going forever and ever and ever with no pattern to it. So it's an irrational number, and it's named after a mathematician named Euler. It's called Euler's number sometimes, and that's why it's e. It's a lowercase e. Now you can also use e as a base in an exponential function. So here's kind of your general equation, y equals e to the power of x. And we use this function to model quantities that grow and decay continuously. One example that gets used a lot is continuously compounded interest in a bank account or investment account. Okay, so let's practice evaluating or using our calculators here to take e to some powers. First one is e squared. You need to find e on your calculator. I believe you need to hit second and then some key before you find e. Then you're going to get this little caret key that pops up. E to the power of, type in 2. And we're going to round our answers to 4 decimal places. We get 7.3891. Go ahead and take a minute now to find e on your calculator. In part B, we're going to take e to the negative 1.3 power. So e to the power of negative 1.3. And we get 0.2725 to 4 decimal places. Now, of course, there's an inverse to every exponential equation. The inverse of y equals e to the x is the natural logarithm log base e of x. Remember, logs are actually the inverses of exponential functions. There's a special way to write this log, though. We call it the natural logarithm, but instead of writing log base e of x, we can write it using ln of x. And this is how you usually see the natural logarithm. Just like log base 10 is called the common log and we don't fill in the base, if it's a natural logarithm, you'll see ln of x. But just so you know, it really means that our base is e. It's really a logarithm with base e. Now you will also find an ln key on your calculator, and this is the key you're going to use to evaluate natural logs. When you graph these two functions, e to the power of x and ln of x, here's what you get. You get an exponential equation, e to the power of x, exponential graph, I should say. And then, of course, the inverse is the mirror image. So the ln of x looks like this graph here. Okay, so now let's practice evaluating some natural logarithms. Take the ln of 4. Just type ln 4, and to 4 decimal places, you should get 1.3863. Try the ln of 0.05, and we get negative 2.9957. Now, once you know how to calculate these, of course, we can practice solving equations involving e's and natural logs. Okay, so now let's write an equivalent exponential or logarithmic equation. In part A, we've got e to the power of x equals 5. We want to rewrite this using logs, using ln. So how can I transfer this into a logarithm? Well, my base is e, so it's a natural logarithm, ln of 5 equals x. Remember that your logarithm is always going to equal the power, so the ln of 5 equals x means the same thing as e to the power of x equals 5. Now in part B, we're starting with a natural logarithm. Ln of x is approximately 0.6931. How can we write it in exponential form? So taking the logarithm, rewriting it in exponential form. Well, remember that your base of this logarithm is e. So it's base e, here's your power, and it should equal x. So e to the power of 0.6931 is approximately x. So now we can go back and forth from base e to natural logarithms. Let me show you a couple more examples here. E to the power of x equals 6. So that means that the natural logarithm ln of 6 equals x. Your logarithm is always equal to the power. In part D, you're starting with the logarithm. We want to rewrite it in exponential form. So your base is e to the 0.5352 power is approximately x. Okay, now here are two facts that we know. These kind of also stem from the properties of exponents, but they're also inverse operations. So if you take the natural logarithm of e to the x, you get x. And that makes sense because your base is e, your power is x, and it equals e to the x power. So that one makes sense. I always think of it this way. The natural logarithm and the base e, they're inverse operations. So if you're taking an ln of e, they kind of undo each other. They cancel each other out, and you're left with the power. Number two, the second fact that we have is e to the power of ln of x equals x. And again, when you take base e to the power of ln, these are inverse operations. They kind of undo each other, and you're left with x. Okay, so if you want to, you can cancel them out. We're going to use these facts to help us solve some equations. Okay, so here's the first equation involving our natural base e. Your first step is to get e by itself. But what we're solving for is the x, okay? So keep that in mind. E is Euler's number, 2.718, whatever it was. So E is a number here. Your variable is x. So I'm going to make that note here. Your variable is x. That's what we're trying to solve for. Okay, so step one, get e to your power, whatever it is. In this case, it's a negative x by itself. That is step one. Okay, so what I need to do here first is add 7 to each side of my equation. Undo the negative 7 there. 5 times e to the negative x equals 9. And now I'm going to divide by 5 to cancel out the 5 on the left here. Okay, so I've got e to the negative x power equals 9/5. Once you get e by itself, now we can take the natural logarithm of each side. So that's my next note here. Take the ln of each side. We're using fact number 1 from the previous slide. Okay, so here's what happens. I'm going to take the ln of e to the negative x, set it equal to the ln of 9/5. Now we know that the ln of e to the negative x just leaves me with the power. So negative x equals the ln of 9/5. Divide each side by negative 1. And we'll have our answer. So x equals, now you would go the ln of 9/5, divide that by negative 1, and we get, let me calculate this here, negative 0.5878. Try this out on your calculator and make sure that you know how to type it in. Okay, so to review, we want to get down to this point here where you've got e by itself. Then we're going to use rule number 1. Let me go back to these facts. You can take the ln of e, take the ln of each side, cancel out the ln of e, and you're left with the power. So that's what I did here down in purple. I took the ln of each side, ln of e, they undo each other. They're inverse operations. So I was left with negative x equals the ln of 9/5, and that I could solve for x. Let me show you another example. So 3e to the x plus 2 equals 4. We want to isolate e to the x. So let's start by subtracting 2. Now we have 3 times e to the x equals 4 minus 2 is 2. I'm going to divide each side by 3 so that I have e to the x all alone. So e to the x equals 2/3. Now at this point, once you get e to the x by itself, take the ln of each side, and usually I just kind of sneak it in. I'm going to take the ln of each side. The ln of e to the x is just x. That is rule number 1. And then you've got x equals the ln of 2/3. All you need to do is calculate this. You've got an ln key on your calculator for that. And we get negative 0.4055. Okay? All right, last couple of examples here. This time you're starting with the natural logarithm. So our equation, and we're also going to do an inequality, they involve a natural log. This time we're going to be using fact number 2, or really their properties. Property number 2 from that previous slide, which says if you use the base of e on each side here, we can cancel out ln. Here's what it looks like. Again, I'm just going to kind of sneak it in, but we're going to take base e of each side. So now my equation is actually in the power. E to the ln of 5x equals e to the 4th. I call this taking the base e of each side. I'm not really sure how else to say it. Okay, so we're using a base e on each side, so now ln of 5x is in a power, and 4 is also in a power. Now let me scroll back here. Using rule number 2, I now have e to the ln of some variable here, so I can cancel out the e and the ln. What I'm left with is 5x. So I'm going to cancel out e and ln. I'm left with 5x. It's not in the power anymore. Now it's a whole number here. Equals e to the fourth. Divide each side by 5, and we've got it solved for x. So now you will type in e to the power of 4, put parentheses around it, divided by 5, and we get 10.9196. Okay, so all you need to remember for this section is that ln's and e's cancel each other out. E is always a base, ln's a natural logarithm. Here's the last one I'm going to show you. You've got the ln of x minus 1 is greater than negative 2. I want to cancel out ln, so the inverse of the natural logarithm is base e. So we're going to sneak that in on both sides here. Now, e and ln will cancel out, and I get x minus 1 is greater than e to the negative second. Now, I really don't need parentheses here. I shouldn't have put them in there. X minus 1 is greater than e to the negative second, and now we're going to add 1 to get x by itself. So x is greater than, now we're going to calculate e to the negative second power plus 1, e to the negative second plus 1, and I get 1.31353. That's a 1.1353. Okay, so I want you to try these two on your own. The first one, you need to get e by itself and then cancel out base e. And number 2, you've got a natural logarithm. You need to cancel it out by taking the base e of both sides.